Okay, so as promised, here we have this quadratic equation. So the key to doing this is to recognize that if this wasn't signed, if it was just some variable, you'd be fine, okay? So the book just jumps right to factoring this. I would say pretend that sine of theta equals x, because then what I have is I have 4x squared minus 1, and that factors as 2x plus 1, 2x minus 1. And then I can replace my x backs with sine theta and get right here. This splits up into two possibilities. Maybe 2 times the sine of theta plus 1 is 0, or maybe 2 times the sine of theta minus 1 is 0. Remember, if a product equals 0, then either the first part or the second part is 0. So either sine of theta is minus 1/2 or sine of theta is 1/2. And note in this problem, we're looking for answers between 0 and 2 pi. So how many angles in one rotation will have a sine of negative 1/2? There will be 2 answers here. And how many have a sine of 1/2? There will be 2 answers here. So we're actually looking for a total of 4 answers for this problem. So sine of theta equals 1/2 gives me pi over 6 and 5 pi over 6. This is where sine of theta is 1/2. Where sine of theta is minus 1/2 gives me 7 pi over 6 and 11 pi over 6. So there were 4 solutions. Okay, how about this one? 3 times cosine squared theta equals sine squared theta. This is kind of a silly example because it, well, you'll see. And again, we're looking for examples between 0 and 2 pi. So we have a sine and a cosine. This could be bad news, except remember that the Pythagorean identity helps me relate sines and cosines against each other, and even more specifically, it's sine squared and cos squared. So since this problem had cos squared and sine squared in it, it was like tailor-made to use the Pythagorean identity. So what we're going to do is we're going to transform sine squared into 1 minus cos squared. Now if I move everything over to one side, we get 4 cos squared theta minus 1 equals 0, which is more or less the same problem we just solved. This factors the same way. The only difference is now we're looking for the cosine to be plus or minus 1/2, not the sine. The previous example factored with a 2 sine theta. Now we have cosine thetas, but it's more or less the same thing. We're going to get 4 answers. Okay, and that's just the pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Those are the angles in the standard rotation of the unit circle whose cosine is either plus or minus 1/2. And those are our solutions. Okay. How about this? Sine squared theta plus cos squared theta equals 3. Okay, hopefully we paused, tried to do it. You may have gotten kind of frustrated because there are no solutions. So the Pythagorean identity allows me to say sine squared theta plus cos squared theta. If I replace sine squared with minus cos squared, we just get, so the book has made a typo. So as written at the beginning, there was a cos squared here, right? Now these cos squareds are going to cancel, and you're going to get 2 equals 0, which is just wrong. There's no solution. So I saw this cos squared at the beginning, and I was like, silly book, there's definitely no solution. Okay, so if that was supposed to be a cos squared, there's definitely no solution. It tells me, however, right. So, sorry, let's go back to the beginning of this problem. As written, there was no solution. Pretend this wasn't cos squared, it was just cosine. Then down here, it's just cosine. And now we actually have something that we need to work with, okay? So replace sine squared with 1 minus cos squared. This now gives me negative cos squared theta plus cos theta minus 2 equals 0 if I move the 3 over there. But if instead I moved everything over to that side, we'd have this equals 0. So now I have an equation where cos squared theta minus cos theta plus 2 equals 0. So the trick to solving this is to recognize that cosine theta can be treated like its own variable. Okay? Just pretend x is cos theta. Then this becomes x squared minus x plus 2 equals 0. And that, we would use the, whoops, sorry, I accidentally hit the wrong button. Here we have x squared minus x plus 2 equals 0. For that, we would use the quadratic equation. And we would say x is negative b, 1, plus or minus the square root of b squared, 1, minus 4 times 2 times 1 all over 2a, which is 1 plus or minus the square root of minus 7 over 2. The discriminant is negative, so we conclude there are no solutions. Okay, so there are still no solutions despite the book's typo at the beginning. Okay, so there are no solutions to this one because we ended up with a quadratic that had a negative discriminant. Okay, sometimes there's nothing you can do but use a calculator. The fact that this mixes sines and just plain old x's means we're dealing with two radically different types of functions. We have a trigonometric sine and a polynomial x, and generally mixing two types of functions together is very, very difficult to solve other than just using a calculator to give you an estimate. So really all you can do here is plot the two functions and try to find where is 5 sine x plus x equal to 3. So there's the graph of 5 sine x plus x against 3, and it looks like there's 3 solutions. And you can just use a computer or graphing calculator to find them roughly to 0.52, 3.18, and 5.71. There are genuinely not better techniques to do this. You just need to estimate it using a computer. Okay, so that's the end of that. I'm actually going to go back and do one more quadratic version. So let's come back to this example here. Okay, this one. But I'm going to erase all of these marks and do a slightly different one. So instead of sine squared plus cosine theta, let's suppose it was sine squared plus, how about 3 cosine theta? That should work. So the first thing we're going to do is quadratic identity gives me, instead of sine squared, call it 1 minus cos squared theta. Pardon me. I still have the plus 3 cos theta, and I have the equals 3. I'm going to move everything over to the right-hand side. So 0 is equal to cos squared theta minus 3 cos theta plus 2. Okay. Now, having these cosines around can be a little intimidating. So what if I just replace it with an x? Then I get x squared minus 3x plus 2 is equal to 0. Hey, this actually factors. This is x minus 2, x minus 1. Okay. If it didn't factor, or if you didn't see that, you could just use the quadratic formula and you would get two solutions. Either x is 2 or x is 1. In other words, the cosine of theta is 2 or the cosine of theta is 1. Hey, the cosine of theta can never be 2. It's always between 1 or minus 1. So this is no solution at all. When is the cosine of theta equal to 1, specifically in between 0 and 2 pi? The only time is theta equals 0. So for this example, theta equals 0 is the only solution. But again, just like we did in the typo version of the book, okay, use a Pythagorean identity so that you're only dealing with cosines or maybe only dealing with sines. Now I have a quadratic equation. If you want, you can leave it in terms of cosines. I actually find it pretty helpful to invent a new variable so that I can temporarily forget I'm dealing with trigonometry and just have a nice polynomial that I need to factor. This one factored just fine. If we were dealing with x's in general, I could let x equal 2 and that'd be great. But since x was specifically a cosine, it can't be equal to 2 and therefore it must have been equal to 1. But x equals 1 is not the end of the problem because we want to go back to theta. So now we need to go back and say when is the cosine of theta equal to 1? Specifically in the region between 0 and 2 pi, it's when theta is 0. So this is a good example of a sort of problem that shows up on the midterm a lot. Use a Pythagorean identity, get something that you can factor. You get different factors, and maybe they both give you solutions. Maybe one of them does and one of them doesn't. In this example, one of the factors didn't actually lead to a solution. Or maybe neither of them do. Okay, in the version the book did you, it just didn't have any solutions at all. Okay, so that's the end of, let me skip forward, blah, blah. We did this, this was the graphing one. That's the end of section 7.3. Okay, we're getting comfortable with trigonometric functions and solving equations using them.